Imagine watching a sports highlight in slow motion. Every twitch of muscle, every flicker of a jersey, rendered with cinematic clarity. That's the promise of video frame interpolation. But until now, there's been a fundamental trade-off: speed or quality. On one side, flow-based models like RIFE deliver near real-time performance, processing frames in under 50 milliseconds. But when motion gets complex, large displacements, occlusions, fast-moving subjects, they break down. Ghosting, blurring, lost details. On the other side, diffusion-based methods, like Consec, BB or TLBVFI, produce stunningly realistic frames. They generate textures from noise, capturing fine details and sharp edges. But at the cost of time, tens of seconds per frame. Not feasible for live applications. So is there a way to have both? To get diffusion-quality perception without the latency? Yes. And it comes not from building a new generative model, but from injecting semantic intelligence into an existing flow-based framework. Welcome to SG-RIFE, semantic-guided real-time intermediate flow estimation with diffusion-competitive perceptual quality. Hash the problem: why flow-based methods fail at complexity. Let's dig into the core issue. Flow-based models treat images as grids of pixels. They estimate optical flow, the motion vectors between frames, and warp pixels accordingly. Simple, fast, but fragile. When a pedestrian runs across the frame, or a car turns sharply, the optical flow field becomes unreliable. Pixels are displaced by large distances. The model can't find a reliable match. So it averages, blurs, or hallucinates. And here's the key insight. The problem isn't lack of motion context, it's lack of semantic understanding. Take a look at this visualization. Even when a person moves across the frame, their semantic representation, their identity, shape, and structure, remains stable. Their color signature, their spatial consistency, their high-level features don't vanish. This is where DINOV3, a vision foundation model, comes in. DINOV3 doesn't just classify objects, it learns invariant representations. Even when a subject moves 100 pixels, the model still recognizes it as the same person. It preserves spatial consistency through a technique called gram anchoring, which regularizes the spatial structure of features across large displacements. So why not use that stability to guide the interpolation? That's the foundation of SG-RIFE. Hash the solution: injecting semantic priors into a flow backbone. Instead of training from scratch, we take a pre-trained RIFE model, already optimized for speed, and augment it with high-level semantic guidance. We freeze the heavy components, the flow estimator, if-net, and the context extractor, context-net. Why? Because they're already excellent at motion estimation. We don't want to retrain them. Instead, we inject semantic knowledge at the refinement stage, where artifacts are most common. Here's how it works. We extract dense semantic features from DINOV3, specifically from layers 8 and 11. Layer 8 captures local textures and edges. Layer 11 encodes global object semantics. These are high-dimensional, 384 channels, so we need a way to compress and align them efficiently. Enter Split-FAPM, the split-fidelity-aware projection module. Split-FAPM has two stages. First, pre-warp compression. We split the DINO features into two branches. A feature branch that extracts task-specific features. A modulation branch that predicts affine parameters using phi-LM, feature-wise linear modulation. The result? A compressed 256-channel semantic representation, aligned with the task, but lightweight enough to warp efficiently. Second, post-warp refinement. After warping, the features often suffer from spatial discontinuities, gaps, misalignments. So we apply a residual block with two key components: depth-wise separable convolutions to repair spatial breaks. Squeeze end excitation, SC, blocks to recalibrate channel importance, suppressing noise, enhancing meaningful signals. No batch norm. Why? Because it disrupts motion statistics. We use GLU instead of RALU to match the activation behavior of DINOV3. Now the features are ready to be injected. But here's the catch: semantic features and pixel-level flows don't align perfectly, especially near occlusions. That's where Deformable Semantic Fusion, DSF, comes in. Hash Deformable Semantic Fusion, soft alignment with dynamic corrections. Traditional warping is rigid. But real motion is. Near occlusion boundaries, where a car hides behind a tree or a hand crosses in front of a face, the flow field is often wrong. So we don't just warp the semantic features. We correct them. DSF uses modulated deformable convolutions, DCNV2, a technique that lets the network learn offsets and modulation scalars to adjust where features are sampled. Here's how it works. 1. We warp the compressed DINO features using RIFE's bidirectional flow. 2. We refine them with the Split-FAPM refiner to fix spatial breaks. 3. Then we use the refined features as keys and values, and RIFE's pixel context as queries. 4. From the query key interaction, we predict dynamic offsets and modulation weights. 5. The final aligned feature is synthesized via deformable convolution, softly correcting misalignments. And the result? A seamless integration of semantic priors with pixel-level motion. We deploy two DSF modules, one at the intermediate encoder level, S2, one at the bottleneck, S3. Each uses grouped deformable convolutions to reduce parameters, efficient, scalable, and effective. We even initialize the fusion gate to 0, letting the model learn when and where to admit semantic influence, only when alignment stabilizes. Why this works, the power of semantic consistency. Now let's talk results. We train on Vimeo 90K, evaluate on SNU film, the gold standard for motion complexity. And the numbers speak for themselves. On the SNU film hard split, where motion is extreme, SG-RIFE achieves an FID of 17.896. That's 8.62 points better than LDMVFI, a diffusion model. And it's on par with Consec. BB, the state-of-the-art generative method. But here's the kicker. SG-RIFE runs in just 0.05 seconds per frame. That's 52 times faster than Consec. BB and 14 times faster than TLBVFI. How? Because we only train 5.6 million parameters, just 16% of the total model, while freezing the heavy DINOV3 and RIFE backbones. We're not replacing diffusion. We're learning from it by injecting its semantic intelligence into a flow-based engine. Visual proof, from ghosting to realism. Look at the qualitative results. Original input frames, a fast-moving cyclist blurred due to motion. RIFE baseline, ghosting on the wheels, smearing on the arms. The model can't track the motion. But SG-RIFE? It reconstructs plausible textures. The cyclist's shirt, the texture of the handlebars, sharp, detailed, coherent. Why? Because it doesn't just interpolate pixels. It understands the object. It knows that the cyclist is still the same person. That the limbs are still connected. That the motion should preserve structure. And so it fills in the gaps, intelligently. Trade-offs and limitations. Of course, it's not perfect. SG-RIFE relies on the frozen, if net for flow estimation. If the flow fails catastrophically, say due to extreme nonlinear motion or severe occlusion, the semantic guidance can't fix the fundamental error. You might get sharp details, but they'll be misaligned. Like a perfectly rendered car, but floating in the wrong spot. So this isn't a magic bullet. But it's a leap forward for real-time applications. Future work. We'd love to test on broader datasets like UCF 101 or ZIF. And we'll dig deeper into ablation studies. How much does Split-FAPM contribute? How effective is DSF? But for now, the core idea is clear. Semantic consistency enables flow-based models to achieve diffusion-competitive quality. Conclusion. The future of real-time video enhancement. SG-RIFE proves a powerful truth. You don't need to generate from noise to achieve perceptual realism. By injecting high-level semantic priors, learned from a foundation model, into a lightweight, efficient architecture, we close the gap between speed and quality. We've shown that semantic guidance can correct the weaknesses of traditional flow-based warping, not by replacing it, but by enhancing it. This isn't just about video interpolation. It's about building intelligent, efficient systems that understand what they're seeing, not just how pixels move. In a world where real-time video is everywhere, streaming, gaming, AR, VR, this is the next frontier. SG-RIFE, where semantic intelligence meets real-time performance. And the future of video enhancement. It's not generative. It's guided. SG-RIFE, semantic-guided real-time frame interpolation. Pan Ben Wang, Qingli Wu, Hanyu Lu, Georgia Institute of Technology. Published on RZIV 2512, 18240, 1v1, 20 Dec, 2025.